Welcome friends. In this video lecture, we will discuss about infinite series. So, let's get started. We will begin with the introduction. A sequence A1, A2, so on, An, and going on, having infinite number of terms is called infinite sequence. And its indicated sum, that is A1 plus A2 plus A3 plus so on plus An plus so on is called an infinite series associated with the infinite sequence. This series can also be expressed in abbreviated form using the sigma notation. That is A1 plus A2 plus A3 plus so on plus An plus so on is equal to summation k is equal to 1 to infinity ak. Now, we shall study about some special type of series which are required in different problem situations. First, binomial theorem for any index. Earlier, we discussed the binomial theorem with a positive integer index. In this section, we state a more general form of the theorem in which the index is not necessarily a positive integer. We know the formula. Here, n is a non-negative integer. Observe that if we replace index n by negative integer or a fraction, then the combinations n, c, r do not make any sense. We now state the binomial theorem giving an infinite series in which the index is negative or a fraction and not a whole number. The formula 1 plus x raised to the power m is equal to 1 plus mx plus m into m minus 1 upon 1 into 2 into x square plus m into m minus 1 into m minus 2 upon 1 into 2 into 3 into x cube plus so on holds whenever modulus of x is less than 1. Remarks. First, note carefully that the condition modulus of x is less than 1, that is, x lies between minus 1 and 1, is necessary when m is negative or a fraction. On the contrary, if we take x is equal to minus 2 and m is equal to minus 2, we obtain 1 minus 2 raised to the power minus 2 is equal to, which implies minus 1 raised to the power minus 2 is equal to 1 plus 4 plus 12 plus so on, implies 1 is equal to 1 plus 4 plus 12 plus so on, which is not possible. Second, note that there are infinite number of terms in the expansion of 1 plus x raised to the power m when m is a negative integer or a fraction. The expression a plus b raised to the power m is equal to a raised to the power m into 1 plus b upon a raised to the power m, which on solving gives a raised to the power m into 1 plus m into a raised to the power m minus 1 into b plus m into m minus 1 upon 1 into 2 into a raised to the power m minus 2 into b square plus so on. This expansion is valid when modulus of b upon a is less than 1. That is, modulus of b is less than modulus of a. Therefore, the general term in the expansion of a plus b raised to the power m is m into m minus 1 into m minus 2 into so on up to m minus r plus 1 into a raised to the power m minus r into b raised to the power r upon 1 into 2 into 3 into so on up to r. Example: expand 1 minus x square raised to the power minus half. Solution: this can be written as this is equal to 1 plus minus half into minus x square plus minus half into minus 3 by 2 upon 1 into 2 into minus x square whole square plus so on. This is equal to 1 plus x square upon 2 plus 3x raised to the power 4 upon 8 plus so on. The second type of series which we are going to study is infinite geometric series. A sequence a1, a2, a3, so on, an is called geometric progression if a k plus 1 upon ak is equal to r for k is equal to 1, 2, 3, so on n minus 1. Particularly, if we take a1 is equal to a, then the resulting sequence a, ar, ar square, so on, a into r raised to the power n minus 1 is taken as the standard form of geometric progression, where a is the first term and r is the common ratio of the geometric progression. Sum of finite geometric progression series is given by Sn is equal to a into 1 minus r raised to the power n upon 1 minus r. Now, we are going to state the formula to find the sum of infinite geometric series. Now, Sn is equal to implies Sn is equal to a upon 1 minus r minus ar raised to the power n upon 1 minus r. For infinite geometric progression, r raised to the power n tends to 0 as n tends to infinity, since modulus of r is less than 1. Hence, ar raised to the power n upon 1 minus r tends to 0. Therefore, Sn tends to a upon 1 minus r as n tends to infinity. Symbolically, sum of infinite geometric series is denoted by S. Thus, we have S is equal to a upon 1 minus r. Example: find the sum to infinity of the geometric progression. Minus 4 by 3, 4 by 9, minus 4 by 27, and so on. Solution: in this series, you can see that the first term is minus 4 by 3 and r is equal to 4 by 9 upon minus 4 by 3 is equal to minus 1 by 3. Also, modulus of r is less than 1. Hence, sum to infinity is S is equal to a upon 1 minus r implies S is equal to minus 4 by 3 upon 1 plus 1 by 3 is equal to minus 4 by 3 upon 4 by 3 is equal to minus 1. The next series in the discussion of special series is the exponential series. Consider the following infinite series of numbers. The sum of the series is denoted by the number e. That is, remark, the exponential series involving variable x can be represented as e raised to the power x is equal to 1 plus x upon 1 factorial plus x square upon 2 factorial plus x cube upon 3 factorial plus so on x raised to the power n upon n factorial plus so on. Example: find the coefficient of x square in the expansion of e raised to the power 2x plus 3 as a series in powers of x. Solution: e raised to the power 2x plus 3 can be written as e raised to the power 2x into e raised to the power 3, which is equal to e raised to the power 3 into 1 plus 2x upon 1 factorial plus 2x square upon 2 factorial plus so on. Now we want to find the coefficient of x square. So, what can we see from here? Yes, the third term, the term containing x square. Thus, the coefficient of x square in the expansion of e raised to the power 2x plus 3 is e raised to the power 3 into 2 square upon 2 factorial, which is equal to 2 e raised to the power 3. Another very important series is the logarithmic series, which is also in the form of infinite series. We state the following result. If modulus of x is less than 1, then log to the base e 1 plus x is equal to x minus x square upon 2 plus x cube upon 3 and so on. The series on the right hand side is called the logarithmic series.